Hello, everybody, and today I would like to talk about topic which is called phase transitions and self-organization. So, what is phase transition? Usually, when the system in one state, it can change this state, and there's some point, a time, temperature, and state can be changed. Okay, there are numerous examples of equilibrium and non-equilibrium systems that exhibit transitions between phase and characteristic special temporal uh, patterns and behaviors. However, if you want to talk about some equilibrium systems, we have to say what is it. Equilibrium system. Value of the state variables where the state variables do not change. Okay, maybe simply to see the right picture. Equilibrium. If we have some point here, this can be in one state, and the state is not changed. Quite understandable and comprehensive, I think. So, what is equilibrium? It's like this. Okay, there are transitions between solids, solid fluids, and gas phases of matter. Diagram. This we can see this diagram here, and sometime before we talked about ferromagnetism, and ferromagnets show also transitions between phases with vanishing and non-vanishing magnetization. Ferromagnets. It looks like this. Very beautiful. Yeah. Vanishing and non-vanishing magnetization. Sometimes it is good to see it by our eyes. Vanishing magnetization. Okay, not like this. There's the different places. In different places, some particles can move differently. And lasers also can produce ordinary light. For example, chaotic light. Chaotic light. By laser. Okay, and as well as laser light, for example, coherent light, coherent light laser. Monochromatic light looks like this. So this is a coherent laser light where the wave go together in one direction, in one phase, and inherent means some different phase. Yeah. So laser can produce ordinary light. It means chaotic light, or as well as laser light, coherent light, and show transitions between this qualitatively different regimes when their pumping energies are changed. So energy changed. Good example we saw before when we have quantum little particles and they move slowly, energy lower, and humans and animals also change their gaits at critical values of locomotion speeds. I think it's quite obvious. And in human societies, there are transitions between fashion trends every now and then. So also some patterns and behaviors of some special temporal patterns and behaviors can be found. So in the following, we will refer to the phases of matter and the characteristic special temporal manifestations of systems simply as phases. So transitions between phases will be referred to as equilibrium or non-equilibrium phase transitions, and system parameters uh, um, that are involved in the phase transition, like this. Will be called control parameters. And we can maybe draw some picture here. And maybe maybe some diagram. And in order to quantify equilibrium or non-equilibrium phase transitions, it is useful to describe systems by means of variables that capture the characteristic properties of phases: solid, liquid, gas, plasma, etc. So to describe systems by means of variables that can capture the characteristic properties of phase, it will be called our order parameters. Order parameters. And let's just maybe make some picture here. So this is our control parameters. This is our control parameters, right? And also, I talk about it later. This is our other parameters. And I will remind you, what is it? What is it like? So, as I said before, we have a system, our systems, and we want to describe. We have some equilibrium or non-equilibrium, phase transitions, and it's useful to describe our systems by means of variables that capture the characteristics properties of phases. So it is called the order parameter, and we put it here, order parameter. And phase transitions can be described also in terms of bifurcations in order parameters. And for example, we have some control parameters here, and we have some others, such like this. It looks like very, very bold actually. To be like this. A moment, I will remove it. So this I will remove. Magic. So here's our control parameters, our order parameters, and now we need to maybe write some critical value point. So this is our this right here, like this, and it is called critical value. So we have a Landau theory of the second order of continuous phase transitions. It tells us, in general, some equilibrium systems phase transition points exhibit order parameters. Let's say we know Landau theories. Landau theory. In physics theory that Landau introduced attempt to relate general theory of continuous phase transitions. Yep. And moreover, the theory predicts that close to phase transition points. So here we can have some point which can critical point. Okay, we can change our directions. The system will change their state. So theory predicts that close to phase transition points, the whole behavior of equilibrium systems can be described in terms of approximately defined order parameters. So that's why we draw this picture here. And that is okay. All quantities of interest can be expressed as functions of these order parameters. So we have some order parameters, and all quantities of interest can be described as functions of these order parameters. And the order parameters of equilibrium systems typically correspond to mean field variables. I mean, we have some different derived from mean field theory, such as average magnetization. So we have a lot of subsystems together and have some variables, and we can use these terms. Okay, average magnetization. Sure, to find this magnetization, average magnetization. Okay. Asia particle magnetization. Okay, maybe next time. In similar spirit, many non-equilibrium systems can be described in the vicinity of phase transition points by means of a few relevant variables, and that's it. So what we can say more? Well, and also can describe this particular by means of a few other parameters. And okay, as pointed out, there are some scientists exist. His name is Haken, and pointed out by Haken, it is helpful to regard other parameters. Of non-equilibrium systems as the counterparts to the other parameters of the Landau theory. Yep. Theory which helps us to formulate to understand phase transitions. And so the question is, what is the reason for the emergence of other parameters? Okay, close to phase transition. This points, two phase transition points, subsystems of many body systems can evolve in a self-organized fashion, and it's important. Due to self-organization, the degrees of freedom of many body systems can be considerably reduced, such that there are only a few degrees of freedom left. Okay? And this remaining degrees of freedom then define low-dimensional phase spaces in which other parameters evolve. So low-dimensional phase spaces exist, and self-organization systems, and we talked about that before, described by nonlinear Fokker-Planck equation. So I want to show you again what self-organization system looks like. So, for example, we have birds, or crystals, or people society, and they have common all together. All these particles together, they give you new behavior and new patterns. So self-organizing systems described by nonlinear Fokker-Planck equation, which I wrote somewhere here. Okay, so this is our nonlinear Fokker-Planck equation, which we wrote before. Again, self-organizing systems described by nonlinear Fokker-Planck equations of these equations typically involve coefficients like dE and dIk, right? Two coefficients that depend on other parameters. And for example, we may deal with a random variable xt. Described by nonlinear Fourier-Plane equation. Let's draw it somewhere here. So let's say we have come on. Okay, we have x and t. Okay, it's our random variable x and t. So for example, we have some particle or some bird or some human and so what this is random variable because it's changing randomly over time. It can be described by nonlinear Fourier-Plane equation here. And we can also maybe draw it here. So we want to know how this probability of okay, this is place where our particle over time. So we want to calculate probability is probability density. How it will change over time. So we say pxt dpxt by dt equals minus some d. So this is our coefficient d by xt by m times what was p probability. I'll tell you later what pm is. P will be defined by m equals average of our xt, average of our x. But okay, so dpxt by dt equals minus sum of the dixtm by sorry xt it's also by dxi dxy and dxk, so it can be high dimensional. So plus, oh, I'm sorry, stupid, totally stupid. Talk about our first coefficient, so not high dimensional, only one. And this is our by dxi plus second coefficient can be described like this. So this is I changing, right? And here we will change I and k. So dik of x tm on pxt. Oh, this is by dxy dxk. That's it. So this is our equation. We can call it, okay, it can be find your equation, it can call it, oh. And that this equation involves an order parameter, m is our order parameter. Order parameter, right? And we also want to say that x, order parameter m, which is defined by m equals square x, or I mean average x, where average x is okay, it's just average x, you know this. So this is how to sum up. Now we know what phase transitions is and self-optimization, and why it is important to know. So some complex systems can be self-optimized. Means okay, some human society or girls or on micro level, there exist some complex systems, and they have self-organization property. For example, properties. Say, for example, birds can fly all together, and they have some order parameters, and they can change their state. So they can go from one phase to another, and it is called phase transition. And they can have self-organization properties, and we can describe in terms of men. We have to know our parameters, and we use nonlinear Fokker-Planck equation to describe behavior of the system. How it is, because we want to know the moment when the system will change its phase. And closer to this moment, to this point, subsystems, they close to this moment. Close to this moment. So close to some phase transition points, the whole behavior of equilibrium system can be described in terms of approximately defined order parameters, which we wrote here. And that's it. Now we know what phase transition is and what is self-organization. So thank you very much for your attention. Next time we will talk about some other interesting topic, which is called stochastic feedback. It is very important. And have a good time, and bye-bye.